Welcome, everybody. How are we feeling? How can... Pumped? Are you pumped? Yeah, he's pumped up. That's what I like to hear. So this tutorial is about software testing for data scientists. The reason I put advanced, so advanced is always going to be subjective, but we're going to go beyond a simple assert equal. We're going to see what's after that. So that's why it's going to be a little bit more advanced. So before we kick off, we have a nice little team today. So we have David. Hello. Woo! David is a senior teaching fellow at Cambridge Spark. Then we have Kevin. Kevin is the CTO of Cambridge Spark. And you can see we all look completely different in those pictures than what we look today. Because those photos were taken a long time ago. Especially you, Kevin. You look really young. Cool. So what are we going to do in this tutorial? Well, we're going to answer different questions. So the first one is my code correct? That's a good start. And that's what unit tests are for. Then the next question is, well, how do we write good tests? Then actually, it's quite boring to write tests. You know, you have to write all those assertions. You have to set things up. Wouldn't it be nice if we could get tests generated for us? So we're going to look at that. And you'll see that it's actually not that easy to do and can be inconvenient. And then finally, we'll look at the real-world situations, right? In practice, we depend on databases. We depend on REST APIs that we have to plug into. How does that impact our testing? So those are the range of topics that will be covered in this tutorial. So there is a bit of a setup to do, and I'll walk you through the outline. So we'll kind of motivate the need for testing for data science. After all, testing was created for software development, so why should we care as data scientists about testing? Then a quick review of the testing tools available, setting the scene. Then we'll deep dive into unit testing using PyTest, which is one of the tools available. We'll talk about why it's good for data science in particular. We'll talk about writing good tests, what are patterns available. And then we'll look at something that sounds really great for dinner parties, property-based testing. And then test doubles and mocking. So it's quite a meaty agenda today. So this is the setup for today. If you've just arrived, please take a photo of this slide so you can do it. I'm going to leave it up for 30 seconds, and then I'll move on. So it's about, I think, 80 or 100 meg. So, you know, there's quite a lot of people in this room. We'll see how the network goes. But that contains essentially all the files that I'll be using this tutorial for the demos. There's a series of exercises as well. There's a notebook, and there's some data sets. So that's why it's taking a little bit of space. Cool. All right, let's go through. So what's the background? So we're going to look at a data set made out of Kickstarter campaigns, and we're going to build a model around it. So a Kickstarter campaign essentially is a way to crowdfund a project, and a project might have different features, like the amount to raise, the category of the project, which region this project started in, right? So those features. And we'd like to build a model that's going to predict whether a Kickstarter campaign is successful or not, okay? So we're going to write a bunch of code to do the modeling, and that's going to create the question of, well, how do I test this whole thing? Cool? So I'm going to jump into a notebook. Cool. So once you've downloaded the Git repository, you should see something similar to that. And we have a notebook, which I'm just going to kick off. Cool. We'll zoom in. So what you'll see is that we've got a zip that contains a bunch of data. I'm going to get pandas, our favorite friend, to load this up. And then we can get a feel for what the data is. And what you'll see in this data, there's different columns. So there's the photo for the campaign, there's the name of the project, there's the goal, so that's the amount to raise. There's a bunch of interesting features like the country, the currency, then the deadline, so that's a timestamp on when the campaign is going to close, when the campaign was created, when it was actually launched, when the post was created, and then a bunch of JSON kind of data that represents further information like the category, the URL, background image, and so on, right? So this is the real deal. This is not like a made-up CSV file with numbers. This is a data frame that contains text and JSON, and we're going to have to build a model, process that, and test it, okay? Cool. So that's the scene. So what you can do in the command line, so you provide it with a script called run.py, and you can run it, and by providing the argument train, essentially what it's going to do is to train the model on the training set using, I believe, logistic regression, and then it's going to serialize this model into a joblib file, okay? So just to give you a flavor of how things are structured here. So I've got a model. This is the implementation of my model. Okay, it's a class. It's going to create, so hopefully, who came to Kevin's tutorial earlier? Yeah, great. So Kevin did a fantastic job at explaining how to use scikit-learn to build a modularized pipeline of a series of transformers which can reuse. So those transformers might be doing some feature extraction. They might take some JSON data and extract, for example, the category, or they might be doing some translation between the country to its region. So that's all the code that is being set up. So that's my pre-processing step, and then training model, logistic regression, and then I can predict. Okay, so that's the code for the model. It's available in the model.py file. Okay. Now, as you can see, all of this code heavily makes use of different pre-processing steps. So there is a categories extractor, a country transformers. What's all of this stuff? How do we know this is correct? Is it doing the right thing? So in this tutorial, we're going to look at, well, how do we unit test it all? So if we look at one of those categories extractors, what you'll see is that we have a module called transformers, which encapsulates all the transformers that my model is going to use. The benefit of doing this is that if we have a team of data scientists, they can all reuse transformers that they've created. They can experiment with different models, but we get the benefit of code reusability. So that's why all those transformers are packaged up into a module. And what you'll see, the code is not exactly trivial. There's some business logic. There's some parsing. We're creating some data frames. We're extracting different index. So it raises the question on, is this correct? Okay? So that's the scene. That's the background, the structure of the files. And now we're going to look at what we can do with all of that. Cool. So testing for data science. So first, we talk about testing. What is it we want to test? There's so many things we could test. So on one side, you've got a difference between functional and non-functional requirements. Functional requirements are simply, is it doing the right functionality? Given the input, is it producing the output I'm expecting, right? So for example, does my model output prediction in the expected range? You know, is it 2 categories? Is it 10 categories? If we have a finite set of outputs, is it actually producing a result in this output? So that's a purely functional requirement. The next question you might be wondering, well, I've written all this code that's going to do some pre-processing. It's going to take those JSON objects, extract different attributes, maybe convert it, do one-hot encoding on all of that. So we have complicated business logic that we want to test. So that's the functional part. Now, we also need to worry about non-functional requirements. We no longer live in the days where we have a Python notebook and .predict, something happens. What happens to the model? We need to package it. It's going to be served by some sort of an endpoint, right? So is my model, when it's deployed, can it handle requests? Can it cope to 1,000 requests per minute? Is there a sort of SLA? when I'm asking for a request, do I get a response within a certain amount of time? And for example, the classic scenario of fraud detection, SLAs are going to be important. We want to detect the fraud right now, not in 10 minutes' time. So those are non-functional requirements. And because data science has become complex and more specialized, then we have different specialized skill sets that are handling those different requirements. So non-functional typically would sit with the data engineering team as opposed to the data science team. Now on top of that, you might have other concerns. So it's not just whether is it doing the right thing or not, how well is it performing? So when you git push and you test your model, do you have a performance improvement in comparison to a previous iteration of your model? Can we detect those changes? On what sort of test data set did we test on? Is that going to have an impact on the performance? So those are a series of questions that we need to ask ourselves now that we're dealing with this piece of code that will be deployed in production. So in this tutorial, I'm going to focus on functional requirements and functional testing. Does this look familiar to anybody? So why are we testing? Well, there's different reasons why we want to test, but one of them is we want to avoid this, right? We want to avoid a catastrophic failure in production, right? So who works in a financial service here, right? If suddenly the transaction processing fails, there's going to be a lot of unhappy people out there. So we want to avoid that, right? So testing is about giving confidence that we've got a correct implementation, and building confidence means that we hope to avoid the scenarios where something will fail. Now, unfortunately, things are really complicated, okay? So again, in the past, data science was all hot, it's still hot, but it's kind of more academic. Let's get a Python notebook, it's great, pandas, boom, predict, then what? Today, it's looking like that. So I didn't make this diagram. This was produced by a team at Microsoft at a leading conference on software engineering. So a software engineering conference is not talking about data science, so that's quite cool. And they said actually the data science workflow has becoming increasingly complicated and there's multiple steps involved. So there is, well, the data, that's just one step. You know, what data do we have? Where is it stored? What's the process to collect it? Is in different formats. We've got JSON, we've got CSV, we've got pickle files, we've got joblib files, we've got Parquet. So what's going on there? So there's a dedicated team and specialists that are handling just data collection, right? There's multiple database technologies that allow you to store different data formats with different trade-offs. Now, what about the cleaning step? You know, data is messy. There is unknown values. The schema might be completely messy. We might not have everything we want. So who's responsible for the cleaning part? Then if we are to do any sort of machine learning, then there is labeling of the data. There's feature engineering. What are features that are of interest to your business domain, which is going to have an impact on the model training? So that's Python code that we're going to have to write. Presumably, we have to test it, right? Because it's going to be complex business logic. And only then does the training come in. On like, let's apply some fancy model, let's evaluate it, learn from that, and then go back to the feature engineering step, maybe get the stakeholders involved to collect more requirements and so on. Once you've done that, well, it's on your computer. How do we deploy this as an application for users? Then we need to worry about cloud services. You need to worry about how to wrap this up into HTTP endpoints. Where is it going to live? How do we test that? Who's got ownership of it? And then we need to monitor the request. What sort of requests are users making? What's the output of the model once it's deployed? How do we evaluate that and learn from it? So the data science workflow is really complex. And what's happening is that each of these modules is a series of software and code that we need to test that it's matching functional requirements to build confidence that we have the right implementation. Now, on top of everything I've said, we have to deal with dependencies. We have to deal with libraries that we're going to package in the application. Those will have different versions. They might have different behaviors. There's backward compatibility issues. We have to deal with web APIs, so live system that we're using, which you have no control on. Those behaviors might change. Databases and cloud services. So there's a ton of complexity from here's a data set to a model that is deployed in production. And that makes our life a lot harder as data scientists when it comes to proving that our work is functionally correct. So the challenges. So as I said, many different data formats. Software developers are used to collections, lists, numbers, classes, and objects, right? Those are simple to unit test. It's a well-known problem. In data science, suddenly we have to deal with pandas data frames, JSON objects, which may have missing attributes and so on. So that was challenging in terms of unit testing. We have to work with database and web APIs. So those are dependencies in our code. And those dependencies might have different outputs, depending on which day we run the code. So that's going to have an impact. We're dealing more and more with black box models. So typically something like a neural net. Looks like it's performing well. It's got lots of parameters. But I have no idea of its internal implementation. So when it comes to unit testing, we have this removed from us. We don't have knowledge of its implementation. It's really, we have to kind of do black box testing. So the best we can do when it comes to those models is testing ranges. Because given an input, the output might be non-deterministic, or it might be in some sort of range. So that kind of changes how we have to test. Now, because the data science workflow is so complex, that means there needs to be enhanced collaborations with different specialists. Data scientists and data engineers have to work together. So that means we have to worry about code maintenance, code modularity, code reuse, APIs to kind of facilitate productivity. So those are new challenges. And yeah, it's no longer a notebook. It's now deployed in production for people to use. No worries. This is fine. Everything is burning. It's OK. We're going to look at a series of tools that hopefully are going to be helpful to kind of go towards the path of functional correctness. So why software testing, to summarize? Maybe the least interesting one, find bugs. Of course, that's something that we want to have. There's maybe situation we haven't thought of. We might write a test case for it, and that's going to highlight an issue in the code which we can correct. Okay, so that's kind of bugs in the implementation. More importantly, it's about removing the fear of changes, so doing like regression testing. Let's say you have a fully working model and pre-processing pipeline. If you make change to it, how do you know the behavior is preserved? You haven't introduced a new bug. So testing allows to remove the fear of introducing changes. It enhances debugging process. Instead of having a big fat exception in your console, well, now we're going to have some interesting assertions going to tell us in which scenario things are working or failing. So that kind of helps us in terms of finding the root of the problem. And then it's about increasing confidence before we deploy into production. So that's why software testing is important for the data science workflow. So let's review the tools available in Python before we focus on PyTest and hypotheses. So there's something called doctest. Has anyone heard of doctest? It's really cute. It sounds cute. It's pretty useless, I think, because it sounds good, right? So we all care about documentation. We've always been told documentation is really important. I'm going to look up a function. It tells me what it's meant to do, the parameters, what it returns. That's important. Pylint is going to flag it up if you don't have your docstring. But on top of that, you can include the thing I've bolded. So using how do you call this symbol? The great sign? Let's go for the great sign. 3 great signs, and then it's basically Python code. And just below is the output we expect when this function is executed. Okay? So a doc test essentially allows you to test you're almost kind of testing your documentation. You had a unit test within the documentation. So this is kind of a helpful example to see potentially how this function is intended to be used. Okay? So that's useful, right? You look at it like, well, here's an example of how to use this API. On top of that, it acts as a test. So test is embedded in the documentation. And really, the purpose of that is only to validate documentation. It's not to validate correctness. It's not about being comprehensive about all the scenarios that we want to test. It's just an example. So this is not a tool for functional requirements testing. This is just documentation. And there's no natural fit with a continuous integration or continuous deployment pipeline. It's basically code that is mixed into documentation, and it doesn't test all the test cases. So that's not really a tool that we should care about as a data scientist. However, there is another package called unit-test, which is part of the standard library. So raise your hand if someone's used unit-test. I expect quite a few of you. Yeah, perfect. Allows you to do unit testing in Python. And it's really popular with developers, because the whole philosophy of unit test and the API wasn't designed for Python. It was designed for object-oriented languages like Java. Java has a library called JUnit, which is classes-based with methods, decorators, and so on. That's where the API comes from. So unit test has an OOP API, so that means there's more boilerplate. You have to define a test case, its subclasses, test case, you introduce methods, then you put assertions. The way you put assertion is, again, a method. So this is not as convenient for data scientists that comes from a Python background where you're used to a series of functions. So that's why unit test is less popular in the data science ecosystem, but perhaps more popular in the software development ecosystem, where developers are used to using things like Java, Scala, and C++ that have an OOP API. So there's more boilerplate, and there is limited diagnostics in terms of the assertions available in the unit test package. Now, PyTest is the cool kid in Python, so it's designed for Python. So what that means is simple functions. You don't have classes, you don't have methods, you don't have 20 different assertions as methods. It's just a function call. So it's got low boilerplate, which is what we like. We don't want to spend a lot of time writing stuff. It's Python, it's got to be simple. And then there's a couple of really interesting features which are easy to use. They're also available in unit test, but there's more boilerplate. Okay? So one of those features is parameterized test. So that's the situation where you test for an input and output, but the template of the test is going to be the same. So in practice, you might copy-paste the same test and change the inputs and output you expect, right? Parameterized testing, we'll cover that in this tutorial. What allows you to do is to abstract what's being tested and inject the inputs and output you expect. So it allows you to reduce code verbosity and improve code maintenance. And finally, there's fixtures. So that's the idea of decoupling data from your test or an environment. So sometimes you might have to plug into a database. So you want to have some sort of setup that is available to all your tests, and then you want to tear it down and close the connection to your database. PyTest makes that quite simple, and it's quite an advanced feature. And parameterized testing uses fixtures, and we'll look at that. So let's do a quick demo, just to make sure everyone's on the same page before we look at more advanced things. So in the list of files you provided, what you'll see is that there's a series of exercises that we're going to look through, and then there's different tests. So I'm going to look at unit test, first of all. So this is how I specify the unit test using the unit test library. Everyone's familiar with that. Before you tell me, Raoul, you should use assertions for pandas, I know, we'll cover that. So basically, you specify a class, you subclass it, you define a method, and then you specify assertions using assert equal, which is a method available as part of the test case class. Okay? So when I do that, I can run this unit test. Okay, great. So let's use the command line. Cool. So if you want to run all the unit tests available in project, you can just pass the unit test command. What it's going to do is to run all my tests, including the unit test case here. So what I'm going to do now is to introduce a failing test. So here's another test just to show you what an assertion failure looks like. So I'm going to unit test my country transformer. That takes a pandas data frame and this sort of output that we want to expect. So in this case, what we expect is the output to be SA, which is not going to be correct, but let's run this. And what you'll see, this is an example of a failure that is produced. So in this case here, Europe is now equals to SA. So Belgium The region for Belgium is Europe, and we expected SA. Obviously, this is just for a demo point of view, so my implementation is correct, the unit test is wrong, but you see an example of a test failure. So how does that compare to PyTest? So here's an example using PyTest, and immediately you can see, we've removed the boilerplate, there's no classes, there's no methods, and there's a simple function called assert that we can be using. And I can introduce a failing test. So really simple to write. And when we run that in the command line, what we'll see is also a test failure. So in this case, I'm expecting the result to be other, but we have none that is produced. So let's dig through here. And what we might want to say is fill an A and then other. Cool, so I'll rectify the implementation. Then we'll run a test again. And now all my unit tests are passing. Okay, so using my unit test in PyTest, I highlighted a scenario where my implementation was incorrect. I fixed the implementation, I run the test, and now it's passing. Okay, so the main point here is PyTest, there's low code boilerplate, and that's why it's really attractive for data scientists. Awesome. So let's do some more interesting stuff. So we're going to dig down into PyTest, and I'm going to get you guys to write your PyTest. So here's an example of a directory structure. So that's my preferred approach. My background is more from Java and software development, but it's the idea of separating out the source code versus the test. Because when you come to packaging and deployment, all your source files are available in one directory. That makes the packaging process really simple. Now, another strategy that people tend to use is to have your test module available together with the module in the same directory, right? So I might have my transformers Py module, and the same directory I might have the test transformer Py module, okay? If we have that, that makes it simple from an import point of view, because when you run your test, the module is readily available in the same directory. So that's great. There's no magic required for importing. But it makes the work of packaging the application more difficult, because you have to extract what's source code, what's not, and deploy that. So I prefer to separate them out and decouple them. So quick exercise, just to make sure everyone's in the same mindset. So in this exercise, what I've got is, so this exercise is called test exercise 1.py. And in this exercise, what we want to do is to unit test a transformer. So the transformer is a categories extractor. And what you'll see, there is some decent pieces of code, right? So it's taking a JSON string as an argument. It's parsing it. It's extracting the attribute called slug. It's doing some splitting. It's going to do some validation, and then returning a pandas data frame. So what I want you guys to think about here is, first write a PyTest for this method. So I'll give maybe 3 minutes, an opportunity for everyone to make sure they're comfortable with PyTest. So to recap, PyTest, what you need is essentially you just write a function, and then you specify your assertion using assert. Now, if you want to run it in the command line, you can use the argument called exercises. And what exercise is going to do is to run all the unit tests in the exercises folder. Okay, so if I run this, well, you'll see that some things are failing, some things are passing because they're not yet implemented. So yeah, cool. So give you guys about 5 minutes, write one unit test using PyTest for this exercise, and then we'll walk through it together. instead of 5 minutes, I'm going to give you 3 minutes. I've been told by my team that I should hurry up. When am I supposed to finish? In hour left. Okay. Good stuff. In the interest of time, and I'm happy to publish the solution, so I'll push the solution after the talk. I'll just walk you through sample solution, right? So quite straightforward. So I've got a JSON string here, which is what is getting parsed by my transformer. It's expecting a attribute slug, and then some sort of categories. And the schema for the categories is that you have the main category, a slash, and then subcategories, right? And I'm going to call the method, and then I'm expecting the result to be a list that contains games and playing cards. So those two things. That's what the transformer does. So can I run this from here? Cool. So if I want to run the unit test, if you use an IDE like PyCharm, like myself, you can run it straight from the IDE. Otherwise, in the command line, Python run and then exercises. So who's used PyTest before? So maybe half, and then everybody's unit test. OK, cool. So this is a simple example of how to use PyTest. Now I'm going to carry on, because I really want to go into the more interesting topics. So the first thing is pandas. So far, my extract categories function was returning a list. That's easy. That's supported by PyTest. The assert function can compare and do an equality test with a list. Well, with pandas, things are slightly different, right? So let's look at an example where I've got a test. Cool. And what I'm going to do, so you see in this code, we basically are going to unit test the time transformer. So time transformer takes a pandas data frame. It's going to extract different columns, multiplied by some sort of adjustment. It's going to do some business logic to find out how many days do we have in between the deadline timestamp and the launch timestamp. Okay, so those are numbers. We want to extract the number of days, and that number of days is going to be a feature in my model. Okay, how many days were there available for the whole campaign? So I want to unit test that. Is this transformer correct? So I've created pandas data frame here, which is a sample data. So that's the input. I know what the expected output is. And I just want to assert that the left-hand side is, so what we expect is the same as the result. Okay? So that's what we might wish to write in PyTest. So far, so good. So let's run that. Boom. What we'll see is that the output is not particularly useful. So what we get is a fat exception saying the true value of a data frame is ambiguous. So we're essentially using a pandas data frame in a Boolean expression context. And as a result of that, the diagnostic produced in the console is meaningless. I have no idea what's wrong, what's going on. So to prevent that, and I'm going to make this test fail again. So let's just run this again. So you'll see it blows up. I have no idea what the bug is. I have no idea what's the difference in the expected end result. Now, pandas supports a testing package. And there's asset frame equal, there's asset series equal, there's asset index equal. That allows you to do accurate equality test on a data frame or a series. So this function is called setFrame equal. So if I use that and run my unit test again, what we'll see is that we get something a little bit more useful. Basically, we get a nice trace that says the values are different. The left side, we've got 29. The right side, we've got 129. So now actually, I get an idea of what the problem might be or what the source of the issue is. Okay? So let's fix this test. And now if I run it again, we'll see everything is going to pass. So what's the story here is that as a data scientist, you use pandas. Pandas is our favorite library, right? There is specialized assertions that you can use that gives you meaningful diagnostics. Okay, so if you didn't know about them, then you now do, and I encourage you to use them to check that your data frames are correct. Cool. So the next topic is parameterized test. So it can be quite repetitive to try for different inputs and check for the same outputs, right? So for example, here, I've basically checked one input. If I want to check for different cases, maybe the deadline is 0, the timestamp is 0. You know, if I'm paid by lines of code, this is beautiful. I can just copy that, you know, put zeros, and then zeros and zeros, and test transformer, 0 timestamp. Actually, I have no idea what that's going to do. Cool. YOLO. Cool. Well, something's right in the code. It's good stuff. But you see, now if I have to come up with yet another scenario that we want to test, again, I have to introduce lots of code duplications. So parameterized testing is the solution to that. It's the idea that clearly there's a template here, right? So there's the sort of setup with the inputs. I had some sort of basic transformation. Then there was a step where I'm doing invoking different functions, and then my assertions. The whole thing can be parameterized with the input and output that I want to check. So rather than use code duplication, we can create a template and then pass on the inputs and outputs. So that's what parameterized testing is. Let me show you how it looks like in PyTest. Whew! Isn't that sexy? Fortunately, we're going to make less money because there's few lines of code, but it's more maintainable, so everyone's going to be happier. So let me explain a little bit what's happening. So the first thing you'll notice is that I've created a list here with the different scenarios that I want to test for. This list contains tuples. Okay? So you'll recognize the tuples with the nice little parentheses. Now a tuple basically has the input as the left-hand side and the expected output as the right-hand side. Okay? So what we can essentially do is to iterate through each element in that list, and we have the input and expected output. So that's the setup part. So that's nice because you may collect those requirements from the business, right? The business might tell you, given this input, that's the output I'm expecting. That's great. You cannot translate those requirements into simple Python code. And then comes the dark magic. So the dark magic is this part. So that's using a decorator, so a language feature in Python. And what this decorator says is, first, so this is the awkward part, you have to provide a string. And this string is essentially the list of parameters that are going to be mapped to the input and output. Okay, so that is applied to each tuple in the list. Okay, so clearly we've got a sample data frame and we've got the expected data frame. Great. And that's the list that we're passing. So now what PyTest is going to do, there's some clever stuff going on. It's going to say, great, now I can inject each sample data frame and each expected data frame for all your test cases. So sample df is going to be mapped to this in the first run, then it's going to be mapped to that in the second run, it's going to be mapped to that in the third run, and the same thing with the output. So now, let's just let's run that in the IDE, see what sort of result we get. Cool. And you can see there's 3 tests that are passed. Right? And the reason it's 3 tests is because there's 3 scenarios that I'm testing out. So parameterized test allows you to be more productive, focus on the business requirements, and translate that into code. Yep.
Sorry, can I just ask, so if you have multiple inputs, let's say like some PF1, 2, and 3, would you just have two more things in your tuple?
Correct. Yeah, so you basically have your list of variables in the string, and that's being mapped onto your function definition. But then your tuple size needs to be obviously like the same. Cool. So parameterized test, encourage you to use it. It's a great tool for writing more maintainable tests. The slides has exactly the same code snippet. So I've done this demo. So there is another exercise. Let's look at this together. So in this exercise, what we want to do is to write some parameterized test for the time transformer, which is exactly what I was demoing. So let me show you the sample solution. So again here, I'm basically setting up my test cases. There's a list of tuples. Each tuple contains a pandas data frame with the different inputs that I want to test. And you'll recognize the 0, 0 that I was kind of testing earlier. And I'm setting up the data. So that's the part where you actually need to think more, right? So what are the different scenarios that I want to check correctness for? And that's the painful part, because you have to consciously think what are all the possibilities where things are going to go wrong. And in a bit, I'm going to talk about generative tests to kind of go around this issue. And the template part is the easiest part, right? So once you know what the template is, so I've got a time transformer. I want to apply processing, and then I'm basically going to do an assert that the two pandas data frame are equal. Okay? So let's run that. And what we'll see is that 2 tests were passed because I've got 2 samples I'm testing out for. Okay? So you can combine parameterized tests and the pandas assertions. Okay? All those things can come together. Awesome. Cool. So we've learned about PyTest basics. We've learned about PyTest parameterized test. We learned about pandas assertions, which are absolutely vital when it comes to data science. Now, how do you write good tests? You know, we can go crazy. Let's write tests for everything. It's going to be great. But like, what makes a good test? So the first thing, there is a simple pattern which allows you to structure your test. Essentially, what that makes your test is a bit more readable, more recognizable. That's called a given when then pattern. So it's not a design pattern like structuring software with classes. It's just a skeleton to recognize the behavior of test. So there's the given step, which is your preconditions. So those are the inputs that you're setting up. There's the when step. That's the behavior you trigger. So for example, I'm calling the transformer. And the then step is, what is it we want to assert on? So here is a test that follows the given when then pattern. So I've got my setup, some nice spacing. It's obvious. I've got the part where we're applying behavior. I can immediately recognize that just by looking at the code. And then what is it we want to verify? Okay? So what that means, your colleagues, when they look at your test, they'll like you. Because they'll be like, ooh, this is really simple to understand. I know what's going on. Okay? So that's a good pattern to follow for readability and code maintenance. Now, there's a ton of libraries that allows you to write more declarative tests. So that's basically attempting at bridging the gap between the business language and the code. Okay? So assert B in A and C in A and then A equals 2 is very Python. You need to be a programmer. So someone with more of a business background, if they look at that, because they might be involved in the requirement phase and the test, they might not necessarily be like able to understand what's going on because they'll get bogged down on syntax. Now, what assertion libraries, and PyTruth is one assertion library developed by Google, that tend to bridging the gap. So another way to write this would be to say assert that A contains exactly B and C. And keep in mind here, we've not specified the order, right? So C and B might appear in different orders. So we just care that they are contained into this list, okay? So here's a bunch of examples of assertions available in PyTruth. There is like at least over 100 assertions available. So I'm not going to cover them all. I'm encouraging you to look at this project, especially if, like I'm saying, the business users are involved in the requirements and the testing part, then that can be a helpful way to close the vocabulary. So for example, you can say something like, I'm expecting a string to start with the character A. So that's like writing English. Or a list has a specific length, or something is on 0. So let's look at a quick demo of that. So in the notebook, I've got PyTruth available here. So I've loaded everything, cool. So I'm going to take the first row, this is a pandas data frame, and I'm basically going to set up some assertions on that. So to give you an idea, I want to write that the deadline is non-0. Great, that's passing. Is 0 available? Yeah. So what that says here, and not true that this number is 0. Okay, so there is also enhanced diagnostics. That's what's really helpful. So when things fail, there's a meaningful error message that kind of tells you what's going on. So that's specifically useful if you've adopted continuous integration, you git push, you get a report from your server, then you have like nice error messages that you can quickly pass. Now let's look at this other example. I'm asserting that the blurb contains the word songs, and that's passing. If I was saying lol, actually let's see. Nope, it's failing. And the self-diagnostic that is generated is the text here, original songs and music videos to jumpstart the Kawaii Core World Tour should have contained the word lol, and it's not, so we get an assertion error. Okay? So PyTruth is maintained by Google, so that's a project to look at. Cool. So on top of that, so given when then pattern allows you to structure the test, PyTruth allows you to write more declarative tests that bridge the gap between the business vocabulary and the code. But how do you write maintainable tests on top of all of that? So tests are just code. It's just Python at the end of the day. So we should treat it like Python code for what it is. So here's an example of a bad test. Who likes this test? Okay, no one. Cool. It's good stuff. So what's bad about it? Yeah, one, what do you say? Yeah, test one means nothing, right? So if the test fails, in the console you see test one error. What's that supposed to mean? Yeah, magic numbers, magic variables. What's 5? What's 1, 0? I have no idea. What are we trying to achieve here? Any other idea? Cool. So yeah, it sucks. And there's more stuff that are sucking, which I'll explain a bit. But here's an example of a good test, okay? We're not optimizing for the number of characters, guys, okay? We're optimizing for reading. The test, you'll read it once. It might be read 100 times. So let's optimize for the read, okay? So nice, meaningful test case names, like the gentleman with the nice beard said, right? Test that model predicts correctly with some standard input, great. The constructor of the predictive model, let's use named arguments to explicitly say what is it we're trying to do. Or maybe I should even extract 5 as a constant or variable to say what it is. I've got input features, so nice variable names. We're following the given when then pattern. And more subtly, this assertion, self-assert true, the only thing that's going to do is to tell you that the Boolean expression given as an argument is true or false. But I want to know what's going on, what number did we get, how we compare against the output, right? So this diagnostic is going to be meaningless. It's just going to be true or false. What we want is, well, you wanted 10, but you got 12, or you got 11. So there's an off by 1 error somewhere, so I can go back in my code and see what the issue is, right? So thankfully, with PyTest, if you use assert, you get it out of the box. So that's another reason why you can ditch unit test and use PyTest, right? Because using one function, you get all those enhanced diagnostics out of the box. So what are the best practices? So verbose naming is better. You want to test the behavior, not the implementation. So in the example I had, I was actually accessing an internal field to check the state of my model. So if that changes over time through some refactoring, my tests are going to have to be refactored too. So you want to make sure you test the API so that the internal implementation can freely change and your tests are still working. So that's good. Don't repeat yourself, so code duplication and so on. Parameterized test is the solution for that. Cool. Now, another tool that the software development ecosystem has been using is test coverage. I want to be a little careful about encouraging getting 100%. I definitely encourage getting the green bar. You know, you want your test to be passing. You don't want failing test, for sure. But what test coverage allows you to determine is the lines in your code that were not executed when you run your test. Okay? So that potentially is useful to detect things that you're not testing. But it doesn't mean you've actually tested all the scenarios for different behaviors. It just means those lines of code were not executed. Okay? So it's just an indication. So it's typically integrated as part of a continuous integration pipeline, right? Because if you got zero coverage, that sucks, really, but you don't necessarily mean 100%. You want to kind of get an indication of why it's potentially not tested or tested. So there is a project called PyTest Cov, which is a plugin that integrates with PyTest. It's going to give you some indication of what you're doing. So I'll show you in the command line what it looks like. So I can run a coverage here. And if I run that, what you'll see is this kind of output. So my model.py, which is here, the lines 1 to 62, nothing's tested. And that's because I didn't write any unit test for my model, right? So I could have written a test, for example, on the predict method. Is it in the expected range? I didn't do it. Now, my transformers, you can see there's different parts which I'm not testing. So clearly, between 63 and 74, something is going on. So let's see what I tested. So we'll go to transformer between. Cool, yeah, so that's the time transformer. So this is the code that I was testing, and I showed you a demo earlier that I was writing in test for the time transformer. So that's been picked up. But everything else has not been tested, okay? So that is kind of a useful report that you can take and then write more unit tests to increase the coverage. But again, it's not an indication that your code is fully correct, because you might still be having all your lines of code executed, but there might be certain inputs that trigger different behavior. Cool. So the next exercise is about refactoring a unit test. So let's say I've got a test that is written like that. Then how would you go about refactoring this test? So clearly we can use a pandas assertions. So let's jump through a solution. So this is a test that's better structured, clearly separating out what's the preconditions, what's the code that we want to apply and test, and then what are the assertions. Okay. Now on top of this here, we could have used the assert frame equals rather than kind of manually extract the different bits and bobs and do an equality on that. Okay. Cool. Let's go to something really fancy, which I've got my doubts on how practical and useful it can be. So that's kind of controversial. But I did find a bug in my code by running hypothesis. So actually, there's credit here. The reason I'm giving a big caveat, I don't want everybody to embark on the buzzword bandwagon. Property-based testing, let's all adopt it. It's not that trivial. So, so far, everything I've shown you was it's called manual testing. I have to come up with scenarios that I want to test against. So I'm testing for specific inputs and specific outputs. So that's easy to write. You know, PyTest, boom, given when then, assert, it's all great. It's deterministic, given an input, I know exactly what the output is. It's great. It runs fast, right? Because simple function to execute. So unit tests are meant to be executed fast because when I make changes in my code, I immediately want to know some sort of regression report, right? I want to know now what's gone wrong. I don't want to wait 10 minutes for the whole thing to run and then have a cup of tea and come back, right? I've got a momentum. I want to fix it. Now, there's a massive downside. The downside is, if you think about the integer space, that's an infinite domain, unless we think about an int, like a 32-bit int, right? But there's so many numbers available. We're going to test for one. So it's not really representative of the state space available when I write a specific test. There might be things I'm missing out. And typically, it's things like negative numbers. We always think about positive numbers. What if my data that I'm reading from an API produces a negative number, which might be an error code? How is that going to impact my implementation? So we don't really think about this kind of stuff, right? So, because it's unnatural. So manual, lots of pros, easy to set up, but might not be checking the full spectrum of the space. Generative test is the idea that unit tests are being created for you. The inputs are generated, so you don't have to worry about that. Ooh, that sounds cool. So the pros is that potentially it's way more comprehensive because we can navigate and search a wider state space. Okay? So that's the big benefit with generative test. The big cons is that it's harder to write. So if I give you guys a bunch of inputs, you don't know what the outputs are. So how can we write an assertion? We can't. We can't say, given X, we expect Y. You can't do that because you're generating inputs. You don't know what the outputs are for those inputs, right? Because you want to test for it. So conceptually, it's really difficult. It's non-deterministic. So a generative test, depending on different runs, might generate different numbers. So you run it once, you might say, I just want 100 tests generated. But what if your state space is 1 billion? You're only going to get a subset of that. The next run, you're going to get another subset of it. So you have this non-deterministic behavior, which is really annoying because if you think about continuous integration, you git push, you want to know exactly what's going on. If you git push the same code, you don't want to have different test reports, right? That's just you're going to go crazy. You're not going to know what's going on. So we want deterministic behaviors when we test. And the other downside is a lot slower, right? So if you generate tests, well, there's some computational activity by default. So it's always going to be slower. I'm not saying it's super slow. I don't have an indication of that, but it's definitely slower than running one test because you generate stuff. So that's the caveat. So now I'm going to look at generative testing a little bit. So the intuition is that instead of providing specific inputs and outputs, you specify a range of inputs. So I want data frames with 2 columns that have integers. That's the range of inputs. Now, it can be any integer. That's going to be generated for us. And you need to specify a rule. And the rule is like, well, what is it we can check? Well, I want to check that any output, I still have a pandas data frame with 2 columns. But because I don't know what the correct results are going to be, I can specify a property, like I'm expecting all the numbers to be positive. That's a property. Or I'm expecting the length of my data frame to be 2. That's another property. That's an invariant that we expect, which we can specify. But it's not asserting a specific input is getting a specific result. It's basically saying there's a sort of property which I'm expecting always to be true. And if you have that, the rule, together with inputs that are generated, then test cases can be generated on the fly. And that's the premise for property-based testing. Let's look at an example. So I'm using a project called Hypothesis, which is open source and available. There's quite a lot of work going on at the moment. It's always moving rapidly. So let me explain these bits of code before I give a demo. So this decorator given is provided by Hypothesis. And everything in bold is what we call a strategy. So you need a strategy to generate inputs. My strategy here is I want a pandas data frame. So there's a pandas extension for Hypothesis, so that's good. As data scientists, we can use that. And it says I want a data frame with 2 columns, one called goal, one called static USD rate. And those 2 columns, I'm expecting floating point numbers. Okay? So I've defined the range of the state space. Definitely data frames, always 2 columns, and the values are floating points. Now, using PyTest beautiful features, then this is injected as the argument to this function as a sample data frame. So what hypothesis is going to do is generate random data frames that have 2 columns with floating point numbers, and that gets passed to my unit test every time it's generated. Okay, so that's how we generate test. Now, the problem I have is I don't know what the result is going to be, because I'm trying to test the implementation, right? So the best thing I can do is to set up a property. So that's an invariant. I'm expecting the length of the sample data frame that is generated, the input, to always be equal to the result. If somehow the result is going to have 3 or 4 or 1 or 0 columns, then something's gone wrong in my code somewhere. Right? So that's an example of a property. So let's do a demo, and I'll show you how I actually found a bug using this stuff. So test transformer hypothesis. Okay. Well, so first I'm going to run the code I was showing to you. So if I run it from here, what you'll see, so let's run this in the console. So using run.py, you can say hypothesis, like that. And what you'll see, let's just look at the output before I go back to the code. What it says is that 100 passing examples, 0 failing example, and I configured the hypothesis to generate 100 examples. You can configure that to 1,000, 10,000 if you want to, but obviously that's going to slow down your test. Okay? So what I was doing is to essentially check for the length. Now, I might want to do something slightly different now. I'm going to set up a different property. I'm going to set up a property that expects the adjusted goal to be greater than 0. Right? So when the pandas data frame generated by hypothesis get pushed down into the transformer here, we'll get a result. And I want to check that that result that I'm expecting is going to be the elements greater than 0. So now if I run hypothesis, what we'll see is that there's some weird scenarios that have not been tested. In this case here, find an assertion error that if the input is 0 and then infinity, we've got some issues. Let's run this again. I wanted to find me the negative numbers. OK, so it's always producing the same test case. The reason it's doing this is when it's failing the first time and you haven't fixed that, it's going to check the failing test the first thing for the next run. So that's kind of a smart way to check that you've corrected that implementation. Now, let's jump to a better example. So to do that, I'm going to show you the sort of strategies that you can create. So at the end of the day, this is only going to be useful if we're able to generate different inputs, whether it's pandas data frame, whether it's JSON, whether it's text, whether it's integers. So using hypothesis, I can import strategies. So in this case, I'm going to import 2 strategies, one called text. That allows me to generate arbitrary text. One called list allows me to generate arbitrary list with number of elements. So this code here essentially says, I want a list of text. Okay? Please generate a bunch of examples. So if I run that, what you'll see, we've got some empty lists that are generated, and then it's going to do weird things like different Unicode characters, because that's always going to create some issue down the line if you're doing some decoding. Empty list, or a list with an empty string, and so on. Right? So this is a strategy that allows me to generate a list of elements. Now, perhaps more interestingly, when it comes to data sciences, we deal with data frames. We learn about doing assertions on data frames, so how do I generate them? So this is the data frame that has 2 columns, and they're both generating floats. So if I run that, what you'll see is that it's generating a data frame with 2 columns, 1 row, with some weird floating point number, and then another one. And if I run this again, it's going to check for the NaN situation, which potentially is going to break things somewhere, right? So those are test cases that you want to make sure your code is robust against. Now, my favorite, and the reason it's my favorite is in practice, you're going to have to deal with JSON data, right? And JSON data is typically a string that represents a sort of nested dictionaries. So how can we generate nested dictionaries? That's the real deal, right? So there is a strategy called fixed dictionary, which I'm going to import. And what that takes as an argument is the structure of your expected dictionary. This dictionary is simple. It has one key called slug, okay? And the value is text, okay? So if I run that, you'll see that it's going to generate some random stuff every time, which is great, because this is the hard stuff that we never think about. So now I've got a tool that generates all those inputs. And when your models deploy in production, there'll be some smart ass that's going to try and call your predict endpoint with some weird characters, right? So you want to make sure you're testing against that. So I'll use this example in a bit for the demo, but another one that I particularly like is the regex. So you can generate text from a regular expression. So for example, here I want to say a string that starts with A, B, and C, and is 3 character long. So every time there was ABBA, my favorite music band. Just kidding. Cool. So you see it generates text that fits the regular expression. So that's quite handy as well, especially if you've got some understanding of what data you expect and there's a structure to it. Now you can combine the whole thing, right? So for example, I can combine the regex strategy inside the dictionary strategy, which is part of a list strategy, so I can generate a list of dictionaries that are following regexes. So all that stuff is really composable. So that's really the power of a hypothesis. So for example, here I'm going to generate a dictionary, which, that's because I'm going to import JSON. Right, so what it's doing is to generate some dictionary that follows this recipe. So the recipe says you need a key called data. The value is going to be generated from this regex. That produces strategy. And map and filter are available in hypotheses. So that allows you to do transformation on your strategy or further filter on the strategy, right? So for example, what I'm saying here is, well, given the strategy that generates dictionaries, I want to generate a JSON string from that. So I'm calling map. I'm passing JSON dumps. Then I'm generating an example. So each example is a string. That is a JSON object, right? So this one line of code generates inputs that are JSON object represented as a string, which follow a specific schema. So that's really powerful. So how do we use all of this stuff? So I've given a couple of examples of how to generate inputs. So you can do it through values, so things like integer, text, and Boolean. You can have strategies for collections, like dictionary and list. Map and filter are available. So that's, for example, if you're generating numbers and you want to filter out the range of the numbers, or there's some sort of property that you want to filter on, that can be useful. Then you can generate your own strategy by implementing an interface in hypothesis, right? So that's all possible. So the problem of generating input is solved. The huge problem that is left is, how do we specify properties, right? Because conceptually, that's difficult. So here's what the community has come up with when it comes to specifying properties. So you can specify things like invariants. So if you know that the result is going to have a specific shape, certain number of columns, for example, that's an invariant. That's something you know is not going to change. You're not testing the output, you're testing a property. Okay? The size of a collection. You're expecting a list to always be of size 3 when you pass it to a pre-processing function. You can test on that. You can't test on the result of the list, but you can test the property. Or, for example, you expect all the values generated to be positive or negative, or in some sort of threshold. You can do that. So that's invariants. Those conceptually, I think, are fairly simple, and you can specify them, right? Now, where things get a little bit more difficult is when you want to do useful stuff. So there's another class of properties called round trips. So that's typically when you have two methods that work together. So if you insert an element into a list, or if you insert something in a database, there's probably another method available that's going to check for containment, right? So you can specify a property that says, when I insert something, I'm expecting it to be available. So those two methods work together. And the JSON example, JSON loads and JSON dumps work together, right? So if I encode and decode something, I'm expecting the same input. So that's a property. If I reverse something twice, I'm expecting the same input. So that's what you can specify. But you see, conceptually, it's not really business logic. It's kind of thinking about some properties and contract. That's why it's difficult to adopt a tool like that. Now, one that is simple, though, is does not crash. So that's basically, you call a function, and you expect no exceptions to be thrown. And a classic example is, if you're trying to do max on a list, if the list is empty, what do you think is going to happen? Value error. It's not possible to find a maximum if something is empty, right? It's impossible. You need at least one element to find a maximum. So those are things that we don't think about. So a hypothesis will generate empty list. And then you're saying, when I call this code, I'm expecting no exceptions to be thrown. But with the empty list, something would be thrown. So that's a different kind of property. Now, one that can be useful if you know what you're doing is called the oracle test. So let's say you're testing the implementation for your code. But there's an alternative implementation that you know is correct that acts as your oracle, right? So given an input, you can pass it to your function. You can pass it to this magic oracle that is always correct. And then you can compare the result of those two. So that's the closest to doing classical assertions. And an example that is brought up, in the community is sorting, right? There's a built-in sorting function in Python. We hope it's correct, right? So if you give an input and you sort it, you'll get a result. If you've written a new sort, you can test the output using this oracle that we know is already correctly implemented. So that's possible. But having those fully working implementation is not always available. So that works when you have an interface and maybe you're coming up with a more optimized version of the same algorithm. Then you can use the less optimized one as your oracle, right? So that's actually where you can use property-based testing, and you'll find problems in the implementation. Right, so let me show you the bug that I found in my code, which I'd never thought about. So that was quite an interesting experience for me. That was quite enlightening. So I want to test my categories extractor. So let's go to the categories extractor and show you the problem. Cool. Right. So here's the categories extractor. Okay. What it does, it takes a JSON string, and the JSON string is like this, right? So it's going to have something called slug, and then it's going to have web, and then Python. Okay? That's the input. What I want as a result is web and Python. Sounds simple, right? So I've written some code for that. Well, this is the code, right? It's basically parses the string in JSON, gets the slug, and if the string is empty, we have a default, which is a slash, and then we split on that, okay? So if the string is empty, we'll get 2 empty categories produced. Okay? So far, so good. So let's try to test for it. So using hypothesis. Ooh, spoiler alert. So this is my test, right? So what I've done is create a strategy that generates a fixed dictionary using slug from regex. So that's a string with the slash, and then dumps that into JSON, so I get a string. Sounds good, right? So far, so good. And then the property that I'm expecting is, the list should always return 2 elements because there's the main category and the subcategory. Cool. So let's run that. Ooh, nightmare. What's going on? Wrong. Well, so let me run that in the, actually, I'm going to copy that in here. Cool. And then we'll get something a little nicer run here. Cool. So what happens if we get this kind of input? Can everyone see? I never thought of that. What if we have a double slash in the value for the slug? My code is returning a list with 3 elements when we have that, right? So that's a situation you'd never think about. And the reason why we have that is if I go back to the implementation, we are splitting on the slash, and there's 2 of them, so we get 3 elements. I was not expecting that. So this is an example of some data that is structured in a way that I would never have thought we would get, but the regex says you split it by 1 slash. Now if I fix the code, which is here, right? Oops. So what I need to do is to say max split by 1. So if we overload the version of split, essentially what I'm saying is split the first time you see a slash, and that's the tail. We no longer parse the tail, because in the tail, there's another slash that we would split on otherwise, and that's what's generating 3 elements as opposed to 2, okay? So if I refactor the implementation now and say split on the first slash and that's it, then I can run the test again, and what we'll see is that it's passing. So this is another test that is failing somewhere else, but let's run it from the solution. Right, so that's kind of a really subtle scenario where hypothesis was actually quite helpful for me to detect a bug. Cool. So how much time have I got left? Ooh, perfect. 10 more minutes. So a related topic to property-based testing, and the bigger picture is we have those kind of contracts that we want to check against, is static type checking. So that's also a property because we're saying we expect a value to be an integer. We expect a value to be a string or to be a list. Now, if you're not aware of this project, it's a good one to check it out. It's called NumPy. That adds static type checking to Python. So when you say a function have a string and can return a string, then NumPy will try and detect those errors before you run your code, right? So that's another form to do testing, not on behavior implementation, but on types and values, okay? That's a cool project to look at. Unfortunately, it's pretty limited right now to things like collections, lists, and values. There isn't support yet for pandas, so you can't specify a type signature for a pandas data frame with 2 columns and a float and get static type checking. You can't do that. But there's progress. So for NumPy, there's an experimental project that is adding support for type checking to things like a NumPy array. So you might want to say, this NumPy array has a D type of integer. I want to detect that before I execute the code. So there is ongoing work. So that's looking good for us. Hopefully over the next, I don't know if it's months or years, there's more and more code checking tools available in the Python ecosystem. All right. Final topic of today. It's called mocking. And where's Tamash? Ah, Tamash. Who's this guy?
You know who he is?
I actually don't know. What's his name?
I'm sure you know.
Who knows what his name is? The guy stretching it back. Huh? Which one, though? The one on the left. They could look quite similar, don't they? Well, I don't know, but this is the concept of a double, right? So when you're in a dangerous situation that might impact your health, what do? You call a double. That's going to take the risk for you, right? So a double is someone that replaces you for a specific situation. Can we have doubles for testing? Yes, we can. Why would we want to have doubles for testing? Here's the situation. You followed good code practices, you're using scikit-learn transformers and pipeline, you've extracted your pre-processing steps. It's amazing, it looks good, awesome. However, as I explained at the beginning of the presentation, the data science workflow is really complicated. We have so many dependencies, databases, APIs, cloud services. So your code is very likely calling a live system somewhere that's returning a result that potentially is helpful for your pre-processing. So in this case here, maybe I'm loading something from AWS. Okay? So I've got a dependency to the AWS client in my code. And now I'm going to try and test process data. Well, how do I test it? Because every time I call this code, it's calling freaking AWS buckets every time. So we're in this situation where in order to test the code, I somehow need to kill this dependency or replace it with something I can control. Because a live system, depending on where the wind is blowing, might have a different output, depending on the day. So how do we get predictability when we have dependencies on live systems? That's the problem that mocking and test double is solving. So there's other issues, right? If I call a REST API, different output, but it might be down. The server might be out of service. That means my test is going to fail. That means your CI system is going to fail. There's fire everywhere. Now, clearly connecting to an endpoint or a service is slow, right? Because it's maybe a call over the network, so we're paying some latency cost, which goes against the principle of unit testing. We want to get failures fast. So those are all the series of issues with unit testing when we have to deal with dependencies, which is the real world that we have in the data science workflow. So what's the solution? A test double. So it's essentially an object that has exactly the same interface as your dependency, but you control it. And you can say what you want it to return or how do you want it to behave. So it's a way to replace a dependency with something you have control over. And the benefits is that it's fast and you have predictability. So the output is always deterministic. Now, before I show a demo, it's a big topic. So different popular libraries would provide you with testing suites, which would implement doubles. So Moto, it's a testing library for Boto, which is a way to interface with AWS. So essentially all the different servers, like connecting to S3, there is a double that doesn't actually connect to AWS, but returns a pre-canned result, but it's got the same interface. PostgreSQL provides you with an in-memory database, which you can set up and tear down for the test, so you don't actually have to connect to a live database. And Flask, if you implement endpoints for your models, will provide you with a test client that is not actually making requests to the server. Okay, it's all encapsulated. Cool. So here's an example of how to set up a mock in Python. And then I'll show you a demo. So let's say I've got this preprocessor object. And this preprocessor has a dependency to a DAO, right? So a data access object, so something that interfaces with a database. I don't know what this database is, but I've got an interface for it, right? So that's the benefit of the DAO. Now the problem is the DAO connects to a live system. So I want to kill the dependency and control it. So you create a magic mock. I know it sounds fancy. That's how it's called. And what you can do now is, well, whenever some code somewhere calls the method or the function, in this case, called load data, I want to control the return value. That's something I am setting, so I get predictability. And the return value is going to be data. Okay? So what it does is, whenever load data is called, here's pre-canned information. We no longer need to connect with the live system. And what you can do with mocks is to specify assertions. For example, this function was called once. So that allows you to verify interaction with your code. Okay? So there's many assertions available. You can check how many times a a function is called, whether it's once or multiple times, with specific arguments, or whether it's not called. Right? So that's what a mocking framework will allow you to specify. So that's for verifying interaction. Now on the other side, you can also control the returned value of, for example, a specific exception that is thrown. So those are the two features available. So let's look through an example. So what you'll see is that I've got a transformer here, which is a no-T transformer. So transformer that is actually connecting to a REST API. So it's passing the country as an argument. It's parsing the result from JSON, and then it's returning the region. So for example, for Canada, it's going to, well, for CA, it's going to produce Canada. For BE, it's going to return Europe, okay, the region where the country is associated. So I've got an implementation here which is hard-coded. Unfortunately, that doesn't scale to every country that exists in the world. So I've decided to have my transformer use an API. The problem I've got now is when I run a unit test, I'm depending on the API, which might be rate limited. So my tests are going to be flaky. So using a mock, what we can do is to say, I've got my country transformer. Whenever this function is called, the get region from code, here's a mock. I'm going to specify a side effect. So a side effect here allows me to return an iterable. So that means every time the function is called, we iterate through those values. If you have 1, you use return value, which is what I had in the slide. If you want to call this function multiple times, and you want a different result to be produced every time it's called, use side effect and the iterable. Okay? So the first time it's invoked, it's going to return Canada. The second time it's invoked, it's going to return UK and Ireland. Okay? So I'm creating my pandas data frame, which has country and 2 elements, transforming it. And now what I can check is that this function, get region from code, was actually called. And it's called within the transformer somewhere when the processing is happening. So what I can do now is, thanks to this mock, verify that the correct interaction is happening under the hood without depending on a live system. Okay? So let's run this. And what you'll see is that the unit test is passing, the implementation is correct. And if I dig down to my transformer, what you'll see is happening is actually simple implementation that uses map. And map is iterating over all the elements in the data frame. And to do that, it needs to call get region from code. And that's where my assertion comes in to say it's been called twice with different arguments. Okay? So that's mocking in a nutshell. So really useful technique to essentially substitute dependencies to live system with something you can control and get predictability on. Woo! All right. So thanks for coming to my tutorial. So we're going to have a booth tomorrow on Saturday and Sunday. Come say hi. And thanks for coming. Solutions in one of the breaks, so you can download them and do the exercise in your own time as well.